Okay, so let's start. When we continue, last time we talked about perceptron and what you can get by first proving the perceptron bound and then asking what happens on IID data. And what we established is the following. This is a bit looser statement than what we proved. If P is the distribution over data, x, y pairs, x being in RD and y being plus minus 1. And if there exists a W star of norm 1 that separates in the population the data, the plus class and the minus class with margin gamma. So this is in population, so I wrote almost surely. So think for all pairs xy, there exists some W star that for all pairs xy, there's a margin. And D is an upper bound on the L2 norm of the x's. Again, let's say almost surely. Then, if you run perceptron repeatedly on the same data multiple times until you make no more mistakes. So you're now at the point where you've made all the mistakes you made, and the next time you run through the data, there is no mistake. So we'll say until convergence. Then the expected loss on the new example, right? This is the expected 0,1 loss. Let me subscript L with 0,1 to mean that this is the expected 0,1 loss of this last hyperplane, which is of course a data-dependent quantity, is no more than 1 over m plus 1 times d squared over gamma squared. What I stated in the previous lecture was a version of this with expectation outside, but let's just assume that for all the data, there is a bound on the radius, which is d, and there is a gamma margin in the population. Okay? So we got the result of this part. Any questions?
Yes. Can you remind us why we need to have the norm squared of W star equals 1?
Yes, so because the meaning of gamma, you mean this one, right? Yeah, so the meaning of gamma changes if you allow scaling in W star. So typically they go in the opposite direction. You can either say, I'm going to call gamma equals to 1, and let me figure out what is the shortest vector that will produce that, or fix W star to be norm 1, and then let's see what's the largest gamma. There's a duality. And these almost sure statements I just wrote because I didn't want to put expectation. So everything here, there's a margin in the population. So you never get cats that kind of look like dogs. That's the so there is a sphere. Let's just think of x's coming from the actual sphere. So there are pluses here, there are minuses here, and there is no man's land of gamma, okay, in the population. So there is some distribution here on the sphere, but this is distribution for the pluses, this is distribution for the minuses, and there is some hyperplane that separates them by a margin gamma. Is that clear? Yeah? We're good? So, again, let me repeat that this is the simplest proof of out-of-sample generalization, if you wish, that you can think of. It took 2 lines to prove the margin bound for a perceptron, and then really just rewriting 1 line to prove this last step perceptron convergence. Right? It's really a miraculous. But when you ask a question of how can we generalize this, you start running into problems. And statements of this type for more general classes become really nightmarish. And what I want to do is kind of to give you a sense of what is involved in going beyond such a simple proof for perceptron. So Any questions about this result? Again, let me mention that it's kind of interesting what kind of assumption we put on the distribution. We're not modeling the distribution of the data. We're not saying that this is some hierarchical Dirichlet process that will construct these images, right, for the plus category and for the minus category. Our assumption on the distribution is really focused on what happens at the boundary, because our problem is a problem of classification, of pattern recognition. That's what we care about. And then for the purposes of showing good out-of-sample prediction, I don't really need to assume what happens here, right? I really just need to assume what happens at the boundary. Yes.
So I'm wondering how strong the margin constraint actually is. It seems very strong for high dimensions, because for high dimensional sphere, most of the lines in there.
Yeah, okay, you can yeah, I don't know, like for a uniform distribution or for Gaussian distribution, yes. But if you think of images, for instance, and now you're saying, do I believe that somehow between cats and dogs there is this no man's land? It starts to become more believable, there is margin, right? But I agree that for a uniform, for instance, maybe this is not a good assumption. Okay? Remember that this is a class conditional distribution. This is distribution given the category 1, and this is category given class 2, right? Okay. So, any other questions? No? All right. So what I would like to do is, again, before I get into the mathematics, I would like to draw some pictures and show you some of the difficulties that we're going to be facing. So if you don't like pictures, I apologize. You know, for those who like pictures, let's see these pictures. Also, I'm a bit under the weather, so thanks to whoever came up with Daegu. But if I stumble, I apologize. Okay, so what I would like to think about is a sphere where I have positive and negative examples. So let's say these are positive examples, and now these are negative examples. Okay, and you see that there is a margin, at least in the empirical data there is margin. Okay, you can make it straight. This should be a straight line. Okay, so what do we know about this WT? Well, what we know is that it exactly separated our data. Our empirical data got completely correctly separated because there is no more mistakes to be made, right? You make a whole pass over data set, there is nothing to be correct. So what you know is that it looks something like that, right? It's a particular hyperplane, WT. The WT has a certain length. It need not be this length, but we only care about the sign. So I don't care about, for prediction, I don't care about the length of WT. For the proof I cared about the length of WT. That somehow gave us a measure of how many mistakes we were making. What I would like to do now is to actually say, let me think of WT as being, as living also on the sphere. Right? Again, it doesn't matter, so I'm gonna draw a little bit larger sphere. Let's say. Okay, and then what I'm gonna do, I'm gonna turn the hyperplane and see what the empirical error is for this hyperplane. Right? So here it's 0. and then it's going to be 0 until I hit, if I keep turning until I hit this point, right? As soon as I pass this point, I incorrectly classify this point. This is the first point to be incorrectly classified. So I start turning, so somewhere here there is 1 over n, right? There is 1 out of n mistakes that we start to be making. Maybe it's 2 over n if at the same time I hit another point, right? But like in general position should be 1 over n, right? So now in this region, really there are 0 mistakes. You can do the same thing for this side, and maybe it's a bit longer. And then I'm gonna start making 1 over n mistakes, or 1 over n empirical error, and then 2 over n. So 1 over n, 2 over n, 3 over n, and so forth. You see what's happening? Okay. Now, when I turn all the way, 180 degrees, and I'm really working in two-dimensional situation. In higher dimensions, it's going to be more difficult to visualize this. But if I completely flip WT, then I'm making all mistakes, right? So here I have 1. N over n is the number of mistakes. Right? So in principle, this theorem is about one element in this block, which completely separates the data. It's a range, but we pick a particular one, right? And the way that we got that was through this perceptron correction. Yes? Okay. And you can ask, okay, how about this one? Like if I take this WT, or if I take that W, will that also have a good generalization performance, right? If I take anything out of this region where I make no mistakes, will that also have a good generalization performance? And that turns out to be not such an easy question to answer. It was very easy for that particular WT. If I take any other, let's give it a name, empirical minimizer. It's going to be an empirical minimizer because it minimizes the 0-1 loss. Right? It gets 0 mistakes. Can I guarantee for that there is a good generalization? Now we're starting to get into a kind of the topic of the next lecture. Right? And let me just tell you that to get, so it is possible to get this statement for all of these guys, but the proofs are very difficult. I don't know of a simple proof that would show that result for all of these minimizers. Okay. Even though we were able to get that particular one, it was just like a really miracle. So this I'm gonna call it a profile or empirical profile, right? As you range over all W's, you should think of a function W, L hat of W, right? That's exactly what it was, right? This was a particular 0-1 loss, right? I'm gonna put 0-1, which is 1 over n sum of indicator, whether, you know, sine of W xt, t from 1 to n was equal to yt, or not equal to yt. Okay? That's the 0-1 loss. Yes?
Can we fix the training set at this point? Like this is not for arbitrary training sets of size n, this is for the particular one we trained on, right?
Yeah, so I want to think of, fix the data set, think of this function. Yes, exactly. But then we have to, then at some point we'll have to say, oh, but these were not any data, they were randomly drawn. So they should be representative of our underlying distribution, right? So that's one function. And the second function is L01 of W, right? That's what you want to minimize. That's the one that you care about, right?
Yes, sorry to interrupt, but
Yeah.
a friend says that the live stream isn't working.
Right. So thank you. Thanks for sharing. So how can we visualize this other function? Well, let me draw it here as another sphere. Like radius somehow doesn't matter. I'm just putting it like as a visualization plot, right? Now, so this is the population. That's this picture, right? This picture. So I'm assuming that there is no man's land in the population, which means that there must exist a W star that has 0. Yeah, so there exists some W star. Now, the thing is, I don't know what its location, right? That's the problem. So there is some W star here. And here it is 0. So there is some region, this wiggle room, where it is 0. You guys see that? And then it starts going up. But I have no idea how it goes up. All I know is that it's 0 over some region. I made no other assumptions on the distribution. Let me unroll this picture into something that's maybe more or easier to visualize. So I'm just unrolling this two-dimensional angle. And I'm going to say that my empirical was like this. It was 0, and then it went up by 1 over n, and then 2 over n, 3 over n, 4 over n. So it goes like this, right? This is my empirical profile. I'm just unrolling 2 pi into a line. But again, this is not generalization. That's not out of sample. That's in sample. And what I have here is the W, right? This is the, as I go over the different W's, what is the value of this function? Right, so this is W hat, 0, 1 of W. What I care about is the green one, which is the out of sample. And what I do know is that there is some region of length gamma, and then I don't know how it goes up, right? What I do know is that over some region, there is some wiggle room, again, where it is 0. That's all I know, right? You guys see that? Is it clear? Yes? No? Yes.
Must the line you just drew, doesn't it have to be 0 where it was 0 in the empirical? That has to be the case, though, right? Because we know there is a gap.
So we know that there is a gap, so there exists. So you're saying, is there intersection between these, right? Is that what you're saying? Or this is a superset?
Yes, that's, I guess I'm questioning that.
Okay, so is it the case that if you're saying that if black is 0, then green must be 0? That's not true, right? So you could, on the data, you could be completely separated, but you're cutting through the population mass, right? Yes.
But if black is non-zero, then the green should not be.
If black is non-zero, then under this almost sure assumption, that's true. The green cannot be 0. Right? So black should be, green should be contained in the black, right? That's what. Green should be wrong. Yes. So green should be contained in the black. Good. Very good. So what we do know is that this region of zero green population is inside of the zero black. That's good. Let me redraw this. So now, the question is, I minimize empirical risk, so I get a completely separated data set, which means that I'm here or here. How high can green go if I know that I'm in the separated regime? Right? If I've separated my data, how high can green go? That's essentially the question we're asking, right? If all I know is that I got my empirical minimizer, how large can it be? And so the answer is actually, it's the same. The result is the same, but the proofs are difficult. Right? So I don't know the simple proof that I can show. So what I'm going to do now is I'm going to make things a little bit more general, but this is a good picture to keep in mind. I'm going to make a slightly more general, I'm going to address a slightly more general question. If I know that I minimize empirical risk over some set, how bad can my out-of-sample error be? Right? That's the question. And I'm going to ask this question even in the non-separable case, where you don't know that there is a true zero loss minimizer. By the way, this is very simple, but if I were to start throwing big names at this, the difference between these two curves is exactly, it's called empirical process. Right? That's all it is. The difference between these curves is an empirical process, and what you want to see is how bad can this be? How bad can this difference between the green and the black curve be? Okay, so in general, we're not going to get all the way to zero, right? It is true that with, let's say, deep neural nets, you often go to zero training error, but I want to not make that assumption. I want to stay a bit more general. There is some curve which is the empirical loss, let's say over W's, and then there is the expected curve. Right? What I'm doing is I'm doing empirical risk minimization. So I'm doing W hat is going to be argmin over some set W in F of L hat of W, right? This is empirical risk minimization. And let me go beyond linear functions. I'm gonna think of nonlinear functions. F hat is argmin over some F in F of L hat of F, right? With respect to some loss. So this is with respect to some loss. So let me replace this with arbitrary functions f. And the question is the following. If I minimize L hat of W or L hat of F, I end up here. But what I want to know is the generalization ability of my model that I found. And that is this point. Right? How high is it? That's what I want to know. Is it clear? Clear what I want? And what I'm going to do next is kind of trivial. I'm going to say that if these two curves are this close everywhere, then it's a good idea to minimize empirical loss, because it can't get much, it can't go beyond that amount, right? So let me just write it out in math minus. And let me do it in expectation, although you can do it in high probability over a draw of data. Let me do it in expectation. So what I want is expected L of f hat. That's what I want small, right? Just as before with the perceptron, this is the out of sample performance of my algorithm, right? Of the thing that I trained with data. Yes? Now, what I'm going to do is I'm going to compare it to the L of f sub f. So what is f sub f? F sub f is going to be argmin of L of f in the class f. So remember the bias variance trade-off we finished last lecture with? I'm going to split the two-step distance to the base into how well can I do against a certain class f, and then I'm going to have this leftover approximation here. Okay. Clear what the subject is? Yes.
So here you are comparing the expected loss of your empirical minimizer with your true loss. So I guess my question is like, do you consider the variance of your like training sample drop from your data set? So for example, if the variance is very high, your loss could be like very far away from the expectation. So
yeah. So the question is, why do we do it in expectation instead of high probability? All the statements that I will make today can be made in high probability with the same type of, slightly more complicated, but essentially same type of analysis. I'm doing an expectation just for simplicity. Some terms will drop to 0. Okay, so this is the, if you remember the previous lecture, the bias variance trade-off, this is the estimation error, right? We're trying to do as well as this target class f. So the kind of the standard thing to do is to say, let me just rewrite this as an expected L of f hat minus let me actually let me do this. So this is the object of interest. Let me just look at the random quantity. This is a random quantity in the data. If you remember the first lecture, this is random in the data set, right, because of the hat. I'm going to look at L of f. I'm going to write this as L of f hat minus L hat of f hat plus L hat of f hat minus L hat of f minus, plus L hat of f minus L of f. I haven't changed it. This is equality. I just added and subtracted this term, and I added and subtracted this term. You can actually trace, by the way, this picture is taking place over a class F now. So on the x-axis is the class F. Now, I usually cannot order it, right? I could only order it in this case of a two-dimensional W, right? Then we could wrap it out, unwrap it, right? But in general, this is just in my mind, this picture. So essentially what I'm looking at is, here's the minimizer of L over my class F. So this point is my F sub F. Yes? This point is F hat, sorry. That's the empirical minimizer. So in fact what I'm doing is I'm saying I'm going to write the difference on the green curve, the out of sample curve. What I care is the difference in the height here and here. And I'm going to write it as a 3 kind of step sum. So this difference is the difference between the expected and the empirical of, so it's this difference, right, of F hat. It's this height difference. That's the first term. The second term is the difference between the heights on the empirical curve between F hat and F sub F. And the third one is the difference, this gap, the vertical gap. Right? That's all I'm doing. Okay, but we know that this guy is less than 0 because we minimize empirical loss over a class F. So because F sub F is in the class, it can only have a larger empirical data. So this is, we can drop this as an upper bound. And now the claim is that this term is 0 in expectation. Why? Well, because F sub F is a fixed function. It does not depend on the data. And so the average of random variables minus their expectation is 0. Let me write it out. You take expectation over the data set of 1 over n sum, let's say some loss function of F sub F, xi, yi. I'm doing a slightly different ordering of the variables in the loss function here. Well, that's just, when expectation goes in, it's just average of n of the same things. And that's exactly L of F hat, F sub F. Any questions about this? Should I explain this again? This part? People video this?
Is this the definition of LF or just the happen to be?
Definition of F sub F?
L.
L.
Without hat. Is this exactly the definition of L without?
Yes, this is exactly expected S of L hat of F sub F.
I mean, is the L without hat is defined by expectation of L hat?
L without the hat is defined, L of F is defined as expected loss of F on XY pair, where you draw so think about what happens here. This expectation goes inside. Now everything that's not I doesn't matter. So what you're doing is exactly that definition. You're averaging over a new xi yi pair. it's important to understand this, because if you don't understand this, the next step will not be clear. So let me try again. Why is this true? When expectation goes inside, we have expectation over the draw of the data set of the loss of some fixed function on one of the data points being drawn. The only thing that matters is that data point, the rest I can discard. And that is exactly the meaning of this. I'm gonna evaluate the loss of my function on a pair, randomly drawn from the distribution. Yes?
So I want to rephrase that just by saying that L hat is an unbiased estimator.
That's right. So L hat is an unbiased estimator for any fixed function. For any fixed function. Is it clear? Who is not clear about this? I'm happy to explain again. Everyone is clear? Okay, I will move on, assuming that you understand this. Okay, so we just established that if you take expectation with respect to the data, then this term is 0. And therefore, what we get is, taking expectation on both sides, expected L of f hat minus L of f is upper bounded, because we dropped this term that's negative, and that term is 0 in expectation, so that's upper bound by expectation of L of f hat minus L, I'm gonna put a parenthesis here, L hat of f hat. So what this is saying is that in expectation, the difference in heights between these 2 points on the green curve, on the out of sample curve, is at most the expected gap between the black and the green curves for the f hat. Yes? So why is this not 0 immediately? Exactly, because f hat depends on the data. So we could do this trick when f did not depend on the data, but we cannot do this trick when f depends on the data. And this is really where, in some sense, this is the crux of the difficulty. So I'm going to spend as much time as needed so that we understand this. So let me write this out. So why is expected L hat of f, or did I start with f? L of f hat minus L hat of f hat not, maybe, not 0. Why would it not be 0? By the way, sometimes this is called generalization gap. The word generalization error can refer to many different things, so I'm afraid to call this generalization error. Sometimes people refer to this as generalization error, or this, and so I have to be careful about the names. But this is, in some sense, this is a key object. So why is this the case? Why can't we just work with the same logic? So let's look at what happens. You take expectation of, with respect to the data set, of L hat of f hat, right? So why is that not just expected L of f hat. Well, let's write it out. It's the expected, with respect to the data set, 1 over n sum of L of, well, let's write it this way, f hat of xi comma yi. Right? These are all the same kind of notation. So in this argument, f did not depend on data, and therefore this was the average of IID random variables, which are exactly L of f sub f. But in this case, f hat depends on the data, and it is evaluated on the same data. This is called the resubstitution estimate. And in the language that we're using, the empirical loss is a biased estimate of the expected loss. It's typically smaller than the expected loss because of this dependence. The same situation was here, right? We couldn't immediately relate the minimizer over the black profile. We couldn't just say, oh, that minimizer is going to be okay in expectation, right? Because it could be biased. It could be that that's small, but the out of sample is big, right? So in expectation, it's not the case. This is not the case that this is equal to expected S of L of f hat. Okay? Okay, so pretty much everything that is out there in terms of generalization, using generalization tools to bound, or using different tools to bound generalization error, is about bounding this object. Okay? It's about trying to understand how different can these be. Right? Yes.
Notation question here, the second line is expectation. So it says, oh, makes sense.
This expectation with respect to data set.
Yeah, that's what you mean.
Yeah, because we took expectation here with respect to the data set, right? This expectation with respect to the data set. Yes?
So at any point, are we taking an expectation over P, over the population distribution?
We're taking expectation over the draw of n data points on which we train, which are IID from.
Right.
So there are essentially several ways to now prove generalization bounds for your f hat. The first way, which is what we're going to do for the next few lectures, is to say, you know what, I can't really understand where f hat is, so I can't understand I can't understand this dependence. So I'm just going to replace it with the supremum, or the maximum, over all the f's in my class. Right? So I could always say this is upper bounded by expected max over f in f of L of f minus L hat f. Which is exactly saying, if I could say that these two curves always fall in this tube of size this much, then I know for sure what the gap is, and therefore I know what this gap is, right, between L of f hat and L of f sub f. by doing this, I remove the hat. So think of this as an operation that removes the hat. It removes the dependence of f on the data. And in some sense, we're now closer to this situation where we have a law of large numbers, which says that the average of random variables is close to its expectation, or an expectation is equal to the mean. But probably we'll have to pay somewhere for this taking a maximum. So that's one approach. The second approach that we're going to do later is to say, let's look at particular properties of the algorithm, such as stability, differential privacy, and so forth. These properties tell us something about the dependence of f hat on the data. And if we can limit that dependence on the data, then roughly this is going to be close to zero. Maybe not zero, but close to zero. So what is important to realize is that the reason why this is not equal to zero is because the output of our algorithm can depend strongly on the data. And if it depends very strongly on the data, then this can be quite large. And if we could, in some sense, limit this dependence on the data, then we can try to guarantee that this is small. This is going to be the topic for the next 5 lectures. So. Is that clear? What's happening? Yes.
I have a question over here. So
Yes.
the max is over the difference, not on the
Yes.
first
Yeah.
one.
Sorry. Max over of this difference, right? I'm saying, if I can guarantee that this is small, if I can guarantee that this is small, that's not always the case, but if I can guarantee that's small, then both of these curves are in some sense in the tube. And then I know that green is close, like green of the f hat is close to the green of f sub f. And the way that I do it is by doing these 3 steps, which show that it's enough to compare that to that. Yes?
Okay, so if you don't understand when we look at the generalization errors, why do we take expectations to the sample instead of the population?
But the sample is from the population. So let me say this. So expected, L of f is defined as the expected loss of f of x y over a pair x y, right? So this capital L already captures out of sample, because you have to perform well on a new draw of the data point. But if we put a hat here, then this is a random variable, because it was constructed using data from this same population, but n data points. Now we have to do something about the fact that this is a random variable. And you can either make statements in expectation or in high probability.
But is expectation is respect to the sample or the population? But the ES or just expectation?
Yes, so, okay, so what is this ES? ES is n-fold integral as I draw my training data from the population, right? So this is a random variable in the data, and what this is saying is, in average, I expect this to be okay over a draw of the data, right? And of course, a stronger statement would say, with probability 99%, I'll be okay. Yes?
So that population is not negative, right? Especially how minus
This one is non-negative? Yes, that's
So in that case, I'm wondering whether we could use a Markov about very high probability statement, or if there
yeah, so you get bad tails from Markov. If you want exponential tails, then you want to have something stronger than just Markov. But you could get some weak tails. Good, other questions? Yes?
Does it matter if there's not a unique minimizer?
in this situation, no. It doesn't, for the purposes of this, it doesn't matter. There are some other situations where you can get extra juice from the fact that it's unique, but not of this type. Yes?
Can you just quickly write out what expectation of L F hat is on that sum?
This one?
Yeah.
Yes. Sorry. Yes. This is expectation over the data. Expectation over x, y variable of L of f hat of xi. Sorry, x. Y. Right. That's what it would be. That's a good point. Sorry, we're not writing it down. Right. So what we can do is we can say that this guy is equal to expected over S L of f hat of x I y I. Okay. And that's not the same as this. And the reason is because here we're evaluating on the, we train on the data and evaluate on that data. But here we're training on the data and evaluating on the new point. Yeah? So why is this the case? You move this expectation in by linearity of expectation. Now you've got average of n terms, which are all the same, just by symmetry. And now you write it like that, right? That's exactly that. Because they're all the same. So if you want to understand generalization and the difficulties that are involved in generalization, everything you need to know in some sense is on these two words. At least to understand the difficulties. By the way, how bad can this be? How bad can this be? We know that they're not equal, but how bad can this be? So my claim is that it can be arbitrarily bad. So imagine a f hat which does the following. It will look at the data set, and data will always come as the following. It will always be x and 1. So I will never see a minus 1. I will always see a 1. Right? So my f hat is going to be a memorization system that will say, I've got a collection of cats, let's say. On the new point, the way that I'm going to predict is I'm going to look up, if it was in my training set, I'm going to say a cat. And if it wasn't in my training set, I will just say a dog, always, right? But in my problem, for whatever reason, I only have cats, right? So it will always be a picture of a cat. Now, how good is, okay, maybe this is a misleading setup, but let me do it with numbers. So I can predict 1 or minus 1. My data set will always have x's with some 1. It will be labeled by 1. And all my data will always be of class 1. I don't have any data of class minus 1. So now my algorithm is such that I just memorize the data and I output, if it's in the data set, I output 1. And if it's not in the data set, I output 0. It's a very stupid learning algorithm. So, my claim is that this is horrible. sorry, this is nice and this is horrible. So why is that the case? So what is my loss of the learned memorization algorithm on the data that it has seen? It has zero loss because it outputs exactly the y variable, which is 1, for everything that was given to me, right? So this is 0. How about out of sample? If x, y is not in my data set, which is going to be, for a continuous distribution, that's always going to be the case. For a non-atomic distribution, let's say. I will output -1, and it will not match the y variable, so this is going to be 1, right? So the gap could be huge. So again, everything that revolves around the study of generalization boils down to understanding how different can these really be for the particular algorithm that I have. Okay? And one way to do it is to remove the hats. One way to do it is to say, really the difficulty here is that f depends on the data and it's being evaluated at the data. So let me try to remove the hat. And one way to remove the hat is to pass to the maximum over the class. Is this step clear? Do I need to justify this any further? This step is, when is this step true? This step is true anytime that f hat takes values in f. So what is important is that f hat takes values in this class f. Otherwise it would not be true. So this is true if f hat belongs to f, which is the case when we do empirical risk minimization, right? So here I'm assuming that we're minimizing empirical risk. Yes?
For the case that like all data sets are 1, the example they give, why the left-hand side is small?
The left-hand side is small because my y, I assume that my y, well, here, because I'm going to predict correctly on the data that I've seen, right? Because I memorize my data and I output that y variable that I've got with the data set, right? It's just memorization already. Yes.
But you're going to randomize over all the samples, right? Like
Yes.
some of the sample will include both -1 plus 1.
Yeah. So I'm assuming that my distribution P is such that my distribution P is such that y is. Let me make it a little bit simpler. Forget about the 1. So what I'm saying is, I memorize my data set, and then I do some nonsense outside of the memorized data set, right? With the 1, it was just a way to kind of to say that I'm doing nonsense because I'm outputting -1, and I only see 1s in my data set, and my distribution actually has support only on the +1, right? So my distribution is a delta function in terms of the y variable on the +1. I will never see a -1 in my data set or in my data. I will never see -1, but I will predict -1 regardless and make an error, right? Does that answer your question? I wrote it out in the lecture notes. Yes.
So over there for that equation on the bottom right, so does that indicate that we can choose, yeah, that's one. Does that indicate that we can choose some set of f so that the maximum difference is small, so our performance is like very generalized with that?
Yes. So essentially, what kind of where we go from here is to say, if f is not crazy, we can say that this is small.
So
And therefore, this is small, and therefore, this is small, and that's what we want.
So basically, for most f set, it's not so large.
For many reasonable
Many.
sets, and we will exactly get so there will be some complexity measure called Rademacher complexity, which will exactly tell us, is this a reasonable set? It's just going to be like a test. Is that a reasonable set, f, or is it too large? Other questions? So if for some reason you didn't get parts of this, I urge you to go home and try to understand. This is really the crux of the matter. This is the crux of the generalization question. Why do we expect the trained model to perform well out of sample or not? So let me erase this part. I'm gonna do a bit more drawing. Okay, so let me do a bit more picture drawing. Are these useful or not? The pictures useful? I always try to come up with a model that I can visualize, and then kind of once you get the right model, you can read off many of the things that we see out there. So again, even if it's not correct drawing, but it exhibits many of the kind of right things. Okay, so the green one, and I apologize if anyone doesn't see colors, but this is what I'm gonna. This is my class F. This is my class F, and green is again my L of F. That's my expected performance. And somewhere in this class there is this best F sub F. So kind of the right way to think about this picture is that the black line is a random process. So what do I mean by that? Let me think of L of F sub F, which is exactly this value, right? And let me think of L hat of F sub F. So again, this is the expected loss of f of x on a new point y, and this is the empirical f of f. Well, let me do it for an arbitrary f. Let me think of an arbitrary fixed f. Okay, so these are the two curves. So the black one is L hat of F. Okay, so now I want to do the following. I want to fix an F. And now I'm going to ask, how different are these? So I fixed an F. And I'm going to ask, how different are these? Now, xi's are IID draws. And so closeness of this to that is guaranteed by law of large numbers. And more specifically, the central limit theorem says that this difference should be on the order of 1 over square root of n. Right? 1 over square root. Yes? Can I write large, higher? So I'm going to look at expected L of f of xi, yi, versus the average, sorry, not xi, just x, xi. So, let's see, I'm debating whether to introduce a simplifying notation or not. Let me try. I'm gonna think of L composed with F as a function, and X and Y as some variable Z. So X comma Y will become Z, and L composed with F will become function G. Is that okay? Then I can just write this as a expected G of a random variable Z, and then this part is 1 over n sum of G of Zi. Right? Now you can really see that this is just the average of n random variables, independent random variables, right? Is everyone okay with that change of notation? I'm just tired of writing loss of a function of data. Now I can just say expected G, okay? And then I can say here, the green one is going to be expected G. And this one is, the black one is going to be empirical G of Zi. Okay, so the point here is that I draw Z1 through Zn, IID at random from the population P, and now I have the average of function values of G and the expected. Okay? So now this becomes G sub F, and this becomes some fixed G. And now I'm going to look at the fixed G. So the difference between this and that is on the order of 1 over square root of n by the central limit theorem, right? So this minus that is something like 1 over square root of n. Now this is not a precise statement because this is a random variable, so you can't upper bound the random variable by a non-random variable. So I have to say that the probability that this minus that is, let's say, larger than 1 over square root of n is smaller than something, right? So it's we would expect that the average of random variables doesn't deviate from its expectation by more than something like 1 over square root of n or some constant over square root of n, right? And we'll make this precise. But first I want to show you what's happening. So for this guy, as I draw a different data set, Z1 through Zn, I'm going to get a different black curve, right? So it's a random curve. So think of this F as changing as I change my data set, right? The green curve stays put, doesn't change. The minimizer stays put. This is really only depends on the underlying population, right? Distribution P. But the black curve is a sample-dependent process, right? And it really changes. Think of this as like a kind of waves changing as you change the data set. It's a random curve. Now, for any fixed G, we know that it should be roughly 1 over square root of n away. The black one from the green one should be 1 over square root of n away. And if I take this one, it's also 1 over square root of n away. And if I take this one, it's 1 over square root of n away. So why does it not imply that I have this 1 over square root of n2? Right? So what I do know is that for any G, probability that expected G minus 1 over n sum of g zi being larger than something like 1 over square root of n is small, why does it not imply that for all of them the deviations are 1 over square root of n? Yes?
Because you need the probability of the intersection.
Yes, so the difficulty is that what I want here is that the maximum of the two curves does not exceed, let's say, 1 over square root of n. So what I want is a statement like this: probability that for any g, expected g minus 1 over n sum of g ci larger than 1 over square root of n is smaller than sum. Right? So this is 1, and this is 2. And there is a world of difference between these two statements. And if you understood the difference, then you're already further than most people in this subject, let's say. One is just central limit theorem. It says that for a fixed g, the fluctuation of empirical and around expectation by the central limit theorem is 1 over square root of n. The second one is much more harsh. The second one says, what is the probability, what is the likelihood that these two curves stay close to each other? And it's a much more difficult statement. If the first one always holds, that's the central limit theorem, the second one holds only for reasonable classes. For classes that are not crazy. Questions about this? So again, the first statement says I'm going to fix g, and then I forget about everything that's out there, and I'm just looking through this narrow window. How does the black point go around the green point? Right? And that's just average around its expectation. And that is central limit theorem. But now the second one says, is it true that the green and the black stay in this narrow window, let's say 1 over square root of n? Typically this need not be 1 over square root of n, it could be kind of a different width of the window, okay, of this tube. Again, I remember looking at this during my first year of a PhD, and I remember spending time and looking at the difference between these two. So it is really useful if you internalize the difference between these two. Let me do it one more example, just to show you the difference between these two, right? The first one would be, let's say I flip a coin 100 times. What is the probability that for my coin, the proportion of tails, if these are 0, 1, tail, head, what is the probability that proportion of tails, let's say, is close to 1/2 to within that much, right? And that's central limit theorem. The other one says, I'm going to flip 100 coins 100 times each. And now what is the probability that for all of them, the frequency of tail is within that gap from the 1/2, right? Just a different statement. It's a more complicated statement, right? So again, one says for one coin, the frequency of tails is close to 1/2 over 100 flips. And the second one says, for any, let's say, collection of 1,000 coins, when I do this, and I repeat this many times, I get closeness of the empirical and the expected values. Does that make sense? Okay. So, just to give a few things, again, what we're gonna do next. Let me just make sure that I've covered what I wanted to cover. Okay, and it's all written in the slides, so perhaps I wasn't clear about this. So this max here is really this for all G, right? That's the same max. Because I want for all G this to be, this difference to be small. It's just here it's written in expectation, and that one is written in high probability. That's the only difference. So, what is a Vapnik-Chervonenkis theory? It's just a characterization of when we can say that this is small for binary classification. So it turns out that for binary classification, one can look at F and say, yeah, that's fine, that's small enough. And look at another F and say, no, that's not. For that F, you cannot any idea of how large this can be. But again, the thing to remember is that's not the only way to go, because we already have quite a few upper bounds. So even if you're working with a VC class, which is a Vapnik-Chervonenkis class, which has a very large dimension, and you're not able to prove any sensible upper bound, it doesn't mean that the problem is not doable. It's just that it's not doable through this technique, right? So when people look at neural networks and say, oh, VC dimension of neural networks is too large, and so this term is huge, and therefore this is huge. This is like reversing the order of quantifiers. Right? So it's not true that if neural networks have too many parameters and you're not able to bound this term, it doesn't mean that nothing can be done. Okay? Just to keep in mind. Yes.
So I have a question for 1 and 2. Can we get an upper limit of 2 from 1 using union bound?
That's great. Yes. So that's right. So if G, so what I meant here to write is this G in G. So if this G is a finite collection, then indeed doing a union bound gets you here. And now the question is, that's for the next class, how do you go from finite to infinite? Because we want to work with, let's say, neural nets with continuous weights, right? So how do you go from a finite to an infinite? Clearly, union bound will not work in that case because it's going to be a union bound over infinite. But there are a number of things that you can do. I mean, one thing you can do is to take a weighted union bound, and that will be still meaningful. And another thing is to do is to say, if there is some notion of continuity here over a class, then what I mean by that is it implies some continuity of this curve, right? So in the previous example, remember as we swept through the W's, the empirical was changing slowly, right? It was like 1 over n, 2 over n, 3 over n, right? There's some continuity to this process, which means that if I'm in this direction and I'm in a slightly different direction, things are not crazily different. So this W and the nearby W are really dependent, right? So I shouldn't just count all of these because they're dependent when I do the union bound. What is important is that what is the nature of dependence as I vary the G. So then I can go to large classes G without having to pay for the union bound. Anyway, I will do everything that I said next lecture in much more detail. Let's meet next time.